calculator has a mass of 200 grams. It's kind of an overestimation, but that's okay. If my calculator is sitting on the table, which it is, what is the normal force on my calculator? So there's our table, there's my calculator. I want to know the value of the normal force acting on my calculator. Now when we deal with force problems, kind of like we did with kinematics, it's kind of nice to draw a little sketch. What you want to do is you want to draw all of the forces acting on the object you're interested in. I want to know the normal force on the calculator, so I want to draw only the forces acting on the calculator. I don't care about the forces on the table. I don't care about the forces on the earth. I just want to know what's acting on the calculator itself. Okay? So, ask yourself a couple questions. What's touching my calculator? Table. So, what's the table doing to my calculator?
Pushing out the calculator.
Pushing up. Now we call that the normal force because the table's the surface. Any surface pushing on an object is a normal force. Now gravity, unfortunately, we can't get rid of gravity. There's always going to be gravity. So the force of gravity is always pulling down towards the center of the earth. The force of gravity acts as if all of the mass of the earth was located at the center of the earth. So it's the center of the earth pulling on your object. So the force of gravity will always point straight down to the earth. There's no pushing or pulling. Nothing else is touching my calculator. There's no friction at the moment because there's nothing trying to slide the calculator horizontally. We're not worrying about air pressure at this point in time. That's really not important until we start talking about fluids. So when we look at this, what we're going to be using is our equation for Newton's second law. We need to add up all of the forces vectorially. That means we have to write them in vector notation. And we're going to set them equal to MA. So this diagram where we have the forces drawn on it is called a free body diagram. You want to draw a free body diagram when you solve your problems. The reason why is you want to make sure you get all your forces in your picture because all the forces in your picture must show up in your equation. This equation tells me that the sum of all of the forces, every single force acting on my object, the sum of all of them together determine the acceleration of my object. Okay? So we have to know all of the forces. So in vector notation, we would write the normal force as F normal J hat. Now I don't know the value yet. That's fine. I'm just going to leave it as Fn to represent the normal force, whatever value it happens to be. Force of gravity. Well, we know the equation that describes the force of gravity, mg. So the force of gravity I can write as mg, but I have to write it as a vector. It's pointed downwards. So I need to put in negative j hat. Now this is why I say don't put a negative value in for g. Whatever you see little g, always put in positive 9.8. We're going to put the negative signs in ourselves when we write them out as vectors. So what we have, easily enough, we only have force of normal force in the positive j direction minus mg in the j hat direction equals ma. Conveniently enough, this all takes place on the y-axis, this particular problem. So we can simply say the normal force minus mg. We can take the j hats out of the picture since it's all in the y direction. That has to equal ma for the y direction. But what's the acceleration of my calculator in the y direction? 0. It is at rest at the moment, and it continues to stay at rest. It's not moving. It's not going to move unless I pick it up, which means I exert an additional force on it. So what this means is that the normal force has to equal mg. So in this particular example, the normal force will equal the weight of the object. Now to get newtons, remember Newton is a kilogram meter per second squared. We need our masses to be in kilograms. How do we go from grams to kilograms? Divide by 1,000. So 200 grams will be 0.2 kilograms. G we know is 9.8 meters per second squared. So the value of our normal force, it's not exactly 2, but very, very close to it. .96 newtons. To give you an idea, a newton, this is a newton. It's like an apple. Pick up an apple, that's about a newton. So newtons are fairly small. So the mass of a person is going to be many hundreds of newtons. So just to give you an idea in terms of conceptualizing what a newton is. Questions on this problem at all? I'm going to modify it slightly. Now, my calculator has rubber stoppers on the back to really increase the friction between my calculator and the table. It takes more effort to try to slide my calculator than to slide this one with just the plastic backing, because everyone starts sliding their calculator. Okay, so the coefficient of friction between my calculator here and the table is going to be relatively large. I don't know exactly what its value is. We could figure it out though. We would need to raise the table until it started to slide, and then measure the angle at which it started to slide, and we could figure out the coefficient. For right now, I'm going to go ahead and just make one up, a value of the coefficient of friction. It's going to be fairly large, so I'm going to say it's 0.7. Same question. If I have the table tilted, at an angle of 20 degrees, what will the normal force be now? Okay, so I want to know what happens to the normal force now that the table is tilted. Forces. Again, when we use this equation, we need to add all the forces on the object we're interested in. We're interested in the calculator. So we need to write up some of the forces on the calculator. So what forces are acting on the calculator? Gravity, always straight down.
Friction.
Friction, which way? Up the incline. If you're not sure, ask yourself what would happen if there was no friction. If there was no friction, the calculator would slide down the table. So therefore, friction must be up the table, keeping that from happening. What else? Normal force. And since we're asking for it, we should obviously draw it in. Anytime your object is sitting on a surface, there will always be a normal force. Surface always means normal force. Now, the normal force is perpendicular to the surface. It's not straight up. It's always perpendicular to however the surface is oriented. So the surface being tilted, the normal force will be perpendicular to that tilt. Now, right now, raising the angle to 20 degrees, the calculator is not sliding down the table. I would like to know what the normal force is. Coordinate system. We can use the traditional coordinate system with the x-axis being horizontal and the y-axis being vertical. That's perfectly fine. But it turns out in problems where the axis is tilted, where we have an incline of some sort, it's easier to use a coordinate system that's tilted as well, because if I use a coordinate system that's tilted, so here's my x-axis and here's my y-axis, only one of them will have x and y components. By tilting my axis, that puts the force of friction and the normal force on the axes. So gravity is the only one with a component. Makes it nice. If we use a traditional coordinate system, both friction and the normal force would have x and y components, and just gravity would have just y component. They're both perfectly fine. You can get to the same answer either way. It just makes it easier if you tilt your axis so that you have fewer components to find. Okay, so we need to write all of these in vector notation. So the normal force, for example, we don't know its value, so I'm just going to call it Fn. It's in the y direction, so it's Fn j hat. You okay with that? So if you don't know the value, it's fine. Just call it something and keep going with it. Force of friction. Well, we have a set equation for the force of friction. Force of friction is equal to the coefficient of friction times the normal force. It's in the x direction, so it's I hat. So I'm just going to write everything symbolically right now. Force of gravity. Well, force of gravity is going to have a y component and an x component. The hypotenuse is mg. The vector itself is always the hypotenuse. When you draw in your components, make sure they're parallel to the coordinate system. Which angle in this triangle is 20 degrees? Top one. We had to rotate from a traditional axis up by 20 to get it lined up with the incline. That meant the y-axis also moved by 20. So that top angle is 20 degrees. So our x component is down the incline, so it's going to be negative. How do I get this side? We're opposite the 20 degrees, so sine. So mg sine of 20 degrees, that's the x component. The y component is also negative. To get the y component, this adjacent side, it's mg cosine of 20 degrees. So we have all three of our vectors written in vector notation. When we add vectors together, we all know how to add vectors. How can we add vectors together? You just add everything together and come up with the final answer. You can add all the i's together, then you can add the j's together. But you have to keep them separately. So when I add the i's together, let's see, I have mu times the normal force, and I have minus mg sine 20. Those are my i's. My j's, I have my normal force and then minus mg cosine 20. Those are my j's. according to Newton's second law, the net force has to equal the mass times acceleration. So those are the net forces. That's the sum of every force acting on our object. That has to equal the mass times the acceleration. But the acceleration can have an x component and a y component. What determines the x component of the acceleration? What on the left side equals the x component on the right side? Whatever your eyes are on the left side equals whatever your eyes are on the right side. X components can't determine y components, and vice versa. Whatever you have as the x component on the left side has to equal the x component on the right side. What that means that's the x component on the left side. The x component on the right side is the mass times the x acceleration. So that gives us one equation to work with. The y components on the left side. Normal force minus mg cosine 20 degrees has to equal the y components on the right side. So mass times acceleration in the y direction. Because of the way vectors work, this equation, F equals ma, we can write it as the net force in the x direction equal to mass times acceleration in the x direction, and as net force in the y direction is equal to mass times acceleration in the y direction. X components determine x components. Y determines y. So we can break it down. Always add up all the x components, set it equal to m times the acceleration in the x direction. Y components, set them equal to mass times acceleration in the y direction. Actually, I'm going to take something back here. Well, let's go ahead and finish the problem first. What's the acceleration of my calculator? 0. It's not sliding on the table. It's not moving away from the table. So these accelerations are 0. It's not accelerating along the incline or perpendicular to the incline.
Does it matter if you have mu on the y1, the y equation? Front of the force?
I don't have u in the y equation.
Oh. Can you explain to me why?
Because force of friction was only in the x direction.
Okay.
So by tilting our axis, we put the force of friction all in the x direction, so the mu only ends up in the x equation. Now we end up with normal force in both of them. And that's because the force of friction depends upon the magnitude of the normal force. It depends upon just magnitude. How hard is the table pushing up on the calculator? And that's why normal force is in there in both. So here, normal force. Since this equals 0, that means the normal force in this case needs to equal mg cosine 20 degrees. It's not the same as it was before. It's not mg. When it's on the flat table, it was mg. Now that it's on the incline, it's only mg cosine 20. It's only the component that's perpendicular to the table. So we know the mass is 0.2 kilograms. G is 9.8 meters per second squared. Cosine of 20 degrees. I get 1.84. That's our normal force. The table is not having to push up as hard on the calculator now. And that's because gravity perpendicular to the table is not not the same as it was before either. Questions on finding the normal force? So, as I said before, there's no set equation for normal force. When the calculator was on the flat surface, it equaled mg. On this tilted surface, it equals mg cosine 20. So the normal force will always come from the problem itself, from the setup. You'll be able to solve for it. I want to do something here. Let's use this value for the normal force and solve this equation for the coefficient of friction. Okay? Actually, let's do this. So the acceleration is 0. So bringing this to the other side, I'm going to be lazy here. Normal force was equal to mg cosine 20. Now you can use the 1.84 and plug all the numbers in, that's fine. I'm going to do it this way, because my n's and my g's cancel. Sine over cosine's tangent. So mu contradictory. Mu's 0.36 according to what we just calculated, but I said it was 0.7. Right. 0.7 would be the maximum possible value of the static friction. Static friction, the value of it changes depending upon the forces applied. For example, have you ever tried to push a refrigerator? Try to move it. You can push on it softly, and the fridge only has to push back softly to not move, to have a net force of 0. You push a little harder to keep the net force 0, it has to push back a little harder. Friction does. You push even harder, friction has to push back even harder. The coefficient of static friction is changeable, but it has a maximum possible value. It can't exceed its maximum possible value. Once you exceed the maximum possible value, then motion will occur. You have to exceed the coefficient of static friction between the refrigerator and the floor in order to get the refrigerator to move.
So if you weigh as much as the refrigerator, the coefficient of friction between your shoes and the floor needs to be greater than the coefficient of friction between the refrigerator and the floor. Otherwise,
yeah, because you wouldn't be able to push yourself in harder. Yeah.
We won't have to worry about normal force in liquids, will we?
We will talk about buoyancy later.
It seems like there's always a force to overcome. Once you get the fridge rolling, moving, then it's easier.
That's because the maximum value of the coefficient of static friction is always bigger than the coefficient of kinetic friction.
Okay.
So that's a good observation. That's exactly true. The maximum coefficient of static friction is always bigger than the coefficient of kinetic friction. So it's always harder to start something moving than to keep it moving once you've got it going.
That's why if you're just trying to push on it, you can't move it. But if you give yourself some inertia first to push against it, to get it moving, then you can continue to move it.
Well, the inertia increases your force applied.
Yeah.
In the
I mean, you don't
first
need to have the
instant, then you
friction in
push
your
the
shoes. If you weigh half what the fridge does, but you accelerate yourself and then stop against the fridge, you generated more forces than the friction kinetic force.
Then if you just pushed. Exactly. You're transferring energy from you into the fridge if you've got a running start.
And then maybe your small amount of friction can keep it going because it's
By the way, we could calculate the maximum angle that we could put this table at before it's at the maximum angle before it started sliding? It'd be the same equation, we would just leave the 20 degrees as theta instead. And then, so basically tangent of theta would equal 0.7. So inverse tangent of 0.7 would give us the angle that we could put the table at. So in this case, if the angle was bigger than 35 degrees, my calculator would start sliding down the incline. So let's
Oh, so it's the same.
let's say we have the table inclined to 50 degrees. Now the coefficient of kinetic friction between my calculator and the table is going to be smaller than 0.7. The coefficient of kinetic friction is constant for any given surface, and it is always smaller than the maximum value of the static friction. So let's say it's 0.55. What is the acceleration of the calculator down the incline going to be? Is this still okay? We continue to use the tilted coordinate system. The normal force will still be in the y direction. Friction still in the positive x direction. It's the coefficient times the normal force. Gravity still has an x and y component. I need to change my angle though, since it's not at 20 degrees anymore. It's 50 degrees now. Now, like we did before, we need to add up all the x components of the forces. So normal force doesn't have an x component. Friction has an x component. It's the coefficient of friction times the normal force. Gravity has an x component, negative mg sine 50. Those are all the x components. So this is the net force in the x direction. So that must equal the mass of our object times the acceleration of our object in the x direction. In the y direction, we have the normal force in the y direction, and we have minus mg cosine 50 in the y direction. That has to equal mass times the acceleration in the y direction. As this calculator slides down the incline, what direction is its acceleration actually going to be in? Negative x. It's going to accelerate down the incline. Is it going to accelerate at all perpendicular to the incline? No. One other really good reason why to tilt your coordinate system, it makes it really nice if you tilt your coordinate system such that the acceleration all ends up being only in one direction. With our tilted coordinate system right here, a sub x is the acceleration of the calculator, A sub y is 0. There's no acceleration in this tilted coordinate system in the y direction. Makes it really nice if you tilt your coordinate system to put the acceleration all in one direction. What that means is the normal force is still equal to mg cosine theta. This time theta is 50 degrees instead of 20 degrees, but it's still mg cosine theta. Before doing any calculations, I want to go ahead and substitute this in back over here. So in place of normal force in this equation, I'm going to put in mg cosine 50. Notice anything? What does every term have in common? Just m. That means mass doesn't matter. So I could have not even given you a mass and we could still solve this problem. This means the acceleration of gravity, the acceleration down the incline you should recognize the g sine 50 from when we talked about inclines before. The acceleration without any friction was g sine of theta. Now, we have an extra term because there is friction. So our coefficient of friction is 0.55. G is 9.8 meters per second squared. Cosine 50 minus 9.8 meters per second squared. Sine 50. I get negative 4.0 meters per second squared. That would be the acceleration of my calculator down the incline. That would be the acceleration of anything with rubber backing on this table. Anything that has the same coefficient of friction, regardless of its mass, would have the same acceleration. And that's assuming drag is still insignificant. Drag would change that. Does the negative sign make sense? We called up the incline positive. Acceleration's headed down the incline, so it should be negative. Notice the acceleration. Is it going to change as the calculator continues its path down the table? This table's straight. So the angle's 50 for every part of the table. Coefficient of friction isn't going to change because we're not changing the materials involved. G doesn't change. So this acceleration is constant. Which means we could figure out how fast the calculator would be going when it reached the bottom of the table. We could figure out how long it would take to reach the bottom of the table. Kinematic equations, perfectly valid.
Until you hit the speed of light.
What? Sorry?
Until you hit the speed of light.
Yeah. Our table's not long enough to get that far.
If it what?
Does the coefficient of friction have, like, units?
No, it's just a number.
Okay.
Just a number, no units at all. We'll be doing a lot more examples with forces. And again, like the kinematics, it takes practice on your part to get used to how to solve the problems. General approach. Always sketch a little diagram. Draw your free body diagram. Draw a picture, draw the forces acting on it. Because you need to make sure that each of the forces acting on your object show up in the equations you write. Okay? Add up all the x components of the force, set it equal to mass times acceleration in the x direction. Add up all the y components of the force. Set them equal to mass times acceleration in the y direction. Make any substitutions you can. Like we did here. We solved for normal force, plugged it back in. And we were able to keep working from there. A lot of people psych themselves out and just talk themselves out of knowing how to do a problem without really trying. I want you to make me a promise. You're going to draw a picture with all the forces acting on it. And you're going to write these two equations. In terms of variables, you don't even have to know any of the numbers to plug in. Just in terms of variables. Write these equations out. See if you can make any substitutions. Get to that point, at least. Will you at least try that hard before talking yourself out of doing the problem? Because usually, once you get to this point, you can finish the problem without anything. It's not a problem after that. Just plug and chug. Leave it in terms of variables. Just do everything you can. Make substitutions you can. And then once you get this far, usually you can finish it. If you don't try to get that far, then you're stuck. A lot of people, for example, I could have very well given you this problem and not told you the mass. And a lot of people would freak out. I don't know mass, so I don't know how to do the problem. But if you go far enough, you see that the mass canceled and it didn't matter. So if you just keep going, just keep trying to plug your way through it, it will work out nice.